Good morning, I'm Bici, a researcher of Sapienza, University of Rome, and I'm here to talk to you briefly about a preliminary approach on point cloud reconstruction of bronze statues through oriented photogrammetry. Our approach has been developed and applied onto the Principe Ellenistico, and this research has been possible thanks to the collaboration of our group of research in Rome, me and Francesca Campana, and the research group of Francesco Leali and Francesco Gherardini of Modena and Reggio Emilia University. As reported here, you can see the table of contents that starts from a little introduction of the methods and the tools we have used. Then we are going to see what is the target of our research and how we have attempted to achieve it, focusing on the Principe Ellenistico, the bronze statue we used as a case study. At the end, results and a little discussion about them are briefly reported just before the conclusions. Nowadays, in cultural heritage, the request of 3D textured virtual models is increasing for several reasons. It could be useful for exhibitions or for restorations in order to guide and plan the activities, for applications of augmented and virtual reality, for digital archival, where virtual copies become fundamental, for digital reconstruction of possible missing pieces or lacunae that can be reconstructed virtually and currently may be 3D printed, or for simulations, as in the previous studies we had about postures and stabilities of some statues that were simulated statically and in other conditions. So, reverse engineering is of a fundamental importance in this field. As you may know, there are lots of possible techniques for reverse engineering an artifact, but obviously they have to be selected for each kind of artifact and material. In addition, due to difficulties connected to the particular shapes and geometries we have to front, and to the huge number of artifacts that could be needed to be acquired, it is important to reach a compromise between the accuracy and the speed that has to be as high as possible, and the cost and the easiness of use of the selected procedure. In this way, maybe close-range photogrammetry represents an interesting choice. This technology is used for analyzing photos taken from a short distance from the object, and with algorithms already implemented in dedicated software, we are able to achieve a reconstruction of the virtual model as a point cloud. Compared to other reverse engineering technologies as laser scanning or structural light, the close-range photogrammetry is generally cheaper and with less specific tools. But obviously, being an optical method, it is highly influenced by light conditions, by the surface finishing and the material of the object, and by its possible reflections. The structured close-range photogrammetry is commonly used in architecture, where a virtual structure and a rigorous subdivision of the space become fundamental. Other applications in artifact and artworks in general that are less rigidly structured commonly need huge phases of work and improvement of the results by photo editing and image processing. Our target is the definition of a structured photogrammetry workflow focused on highly complex surfaces, as the one we can find on a bronze statue, sometimes also with a reflective finishing due to the metallic nature of the statue itself. By this workflow, we want to achieve an accurate 3D model comparable to what we can obtain by the 3D scanning. It is important to note that we can use a standard camera, not a dedicated hardware, without any filter or action of post-processing onto the images, trying any way to maintain and guarantee an acceptable level of accuracy, as in the other technologies of reverse engineering. To achieve this, as said, a specific workflow has been developed. It starts from the preliminary analysis of the artifact, studying its geometry, its finishing in every surface, and the material of which the surfaces are composed by. This helps to evaluate difficulties connected to complex, hidden, or shadowed areas, and the possible light reflection. Then, background and light are set, and the camera and its focus are chosen. We have to take care of avoiding direct lights and flashes, thinking also about the possibility of usage of light shields and diffusers. Anyway, for this kind of system, the natural light is always to be preferred instead of using artificial ones when it's possible. Also, polarizing filters can be used, taking care that in the results they can give an altered texture from the original. The third step of the workflow is the generation of a virtual cage around the artifact, in order to divide the space in angular and vertical steps. This gives us the possibility of shooting photos from different registered positions. In each position, the camera orientation, in terms of zenith and azimuth, can be varied, and we can also add orientation and position, increasing the number of photos for specific complex area. Once photos are obtained in every prescribed position in the gauge, they must be aligned using dedicated software as Metashape or Measure, for example. Each user can choose its own specific software between commercial and open source solution. In this way, at this stage, the point cloud of the artifact can be generated, and by this we can obtain the mesh and the correlated texture. Once the virtual model is present, using software like Geomagic, for example, we are able to compare the obtained model with a reference one already available and obtained by other technologies. It is always recommended to perform this comparison because of the huge variety of the artifacts in terms of shapes, geometries, and finishing. So the obtained model has to be overimposed to the reference one, generating color maps of the deviations. These make us able to evaluate the model accuracy, the quality of the reconstructed surfaces, and also the identification of possible local defects generated by the process. Now we can pass to describe the case study and the application on it of the described procedure. Now let me introduce you our case study. In the picture you can see on the right is reported the Principe Ellenistico, the Hellenistic prince. Probably it has Greek or Hellenistic origins, and it can be dated in the 3rd or the 2nd century before Christ. Lately carried in Rome as spoils of war. It was found fragmented at the end of 19th century on the hillside of Quirinale in Rome, probably in the area where ancient Constantine Thermae were. It is a bronze statue made by lost wax casting, and it is more than 2 meters tall for about 180 kilos of weight. As you can see, it represents a naked hero in the classical pose of sovereign or warlords. Currently, you can find him with his mate, the pugilatore, the boxer, in Rome at Palazzo Massimo, that is part of Museo Nazionale Romano. So let's see the application of the developed procedure to the Principe. Starting from the first step of the workflow, we have analyzed the statue, and from this analysis, some possible difficulties and characteristics came out. It has to be always taken into account that the statue is reflective due to the bronze, even it is ancient and marble. It has to be noted that, due to this, the reflection and the surfaces are also not uniform and equal. It has to be evaluated locally in every single area. In addition, the spear represents a very huge difficulty in terms of possible covering and shadowing the near part of the statue. Other hidden areas are right armpit and the inner part of the legs that present quite the same kind of issues. Some part of the feet show, in addition, problems of accessibility, and in the end, due to the height of the statue, increased by a basement, the top of the head presents some issues in terms of lack of lighting and difficulties to be photographed. For what concerns the second step, background and light settings, and the selection of the camera, we were constrained, obviously, to make the photos in the room where the statue is normally exposed, trying to use the natural lights, turning off the artificial ones, and using some diffused lights for the zones that are not well enlightened. Often the relative positions between the camera and the light source have generated difficulties, generally solved with a different orientation of the light source when possible. In some cases, we were able to use white panels to augment the differences in terms of color between the statue and the background. But more than sometimes, the dark background was impossible to be excluded, generating some difficulties in the resulting photos. We decided to not use polarizing filters in order to avoid to influence the texture to be obtained. The reflex camera chosen was an entry-level camera sold by Canon, which specifications are here reported. You can see on the right a portion of a photo made during the photo set. Then a virtual cage has been generated around the real statue. In this case, it is a cylinder that contains the statue with a radius of 2.5 meters and an height of 2.4 meters. We decided to divide this gauge with angular steps of 22.5 degrees and vertical steps of 0.4 meters. This conducted us to obtain 96 positions, and for each we shot one frontal picture with zenith and azimuth equal to 0, and 4 photos with zenith variation at plus and minus 10 degrees and plus and minus 20 degrees from the 0. Only in some complex areas, from certain positions, we had also an azimuth variation with the same range, so plus and minus 10 and plus and minus 20 degrees, increasing the total number of photos, arriving to about 600 photos. Once photos are obtained, we had to achieve the alignment of them and the reconstruction of the photogrammetric model using edges of metashape. Some photos have been discharged due to the reflection and or some bad background conditions, as mentioned before. After this, no relevant difficulties in alignment have been found. And in the resulting model, noise and no real points are present in areas judged before as complex from the preliminary analysis, like the parts around the spear, the head, some parts of the right arm, for example. In order to reduce noise and outliers, due as said to reflection and shadowing, The initial point cloud of more than 20 million points have been filtered with 3 different types of filters. The first filtering operation on the point cloud was an operation of masking, that means the cut of the scene around the statue and all the background. As mentioned, the usage of white panels in the background was possible only for some of the photos. In the other cases, the dark background could lead to wrong reconstruction of points outside the model. The second filtering operation was a filtering by colors. In fact, we have found that the majority of noise and no real points caused by reflection were in defined color ranges like gray-silver, light golden, light brown, and beige. By removing these sets using their RGB codes, we were able to cut 2 million points. The third and the last filtering operation has been manual removing in complex area. And at the end we obtain a cloud, as reported in the lower pictures, of about 17 million points that generated a triangular mesh of 1.4 million elements for the final model, obtained after an operation of decimation. Here you can see the final meshed and textured model. This model has been scaled to its natural dimensions by using one of the sides of the basement as a reference, because its dimensions was known by an easy measurement. Then the model has been evaluated by comparison with an accurate virtual model already available, obtained with a scanner. For obtaining the evaluation, we used geometric control, but we want to highlight again that the user could choose freely other similar software. The reference model we used was an high-resolution model of about 5 million elements, obtained with an Arte Keva portable 3D scanner, whose 3D point accuracy is up to 0.1 mm, and the 3D resolution arrives to 0.5 millimeters. The overimposition of the obtained model to the reference one has been done using a best fit alignment. By this, we could obtain a full color deviation map reported in the pictures, where we can highlight deviations and possible holes. We can see that in the majority of the zones, the deviation is limited in a range of minus 0.7 millimeters and plus 0.7 millimeters are the green zones in the pictures. As expected, the zones outside this range are those judged complex previously. In fact, the top of the head, due to bad lighting and accessibility conditions already mentioned before, resulted outside the range. This spear, in addition, caused, as expected, problems of shadowing and hidden surfaces, especially in the area near to the left arm. Some issues of bad accessibility caused values outside the range in the right armpit and in the inner part of the legs. At the end, bad background conditions and some reflections have led to high deviation in the corners of the basement. Probably all these parts deserve more photos or an improved set of background and lighting conditions to be solved. But anyway, we can say in general that with this methodology, we have obtained a quite accurate model with a not expensive system and surely in a quite fast manner. Let me resume and conclude this presentation saying that the developed workflow revealed to be useful and competitive in cultural heritage field with other procedures and reverse engineering technologies. This is confirmed by the challenging case study we had in bronze and made of complex shapes. The use of a structured virtual gauge led us to accurate results, comparable with other technologies in the majority of the areas. The procedure is not strictly connected to certain software, so they can be freely chosen by the user, obviously knowing peculiarities and performances of each of them. In the future, this comparison of software could be one of the points to be explored by us. Having used a standard reflex camera, really not expensive, and similarly a really cheap set of tools, means that these quite accurate results can be achieved with a non-expensive and user-friendly system. That was one of the requirements we proposed to be accomplished. In the future, we are going to enlarge the set of case studies, varying materials, reflectance, with the target of performing a sort of archival of cases. We are also planning for the future, and we are starting to study the possibility of application of artificial intelligence and deep learning algorithms for performing the masking step. That was one of the more time-consuming steps in order to automatically cut the background scene from the photos. Another possibility that should be explored in the future is the development of procedures that can use also random photos, bypassing or enriching the structured strategy and its output. So, me and all the authors are pleased to thank Museo Nazionale Romano and the persons of Olimpia Colacicchi Alessandri, Ida Anna Rapinesi, Marina Angelini for all their support and help. And I want to thank you for your kind attention. Please, for any question, doubt, or why not, proposal of collaboration, you can find here our contacts. We want also to thank all the Florence Heri-Tech organization and committees. Thank you again and have a nice day.